Hello. Again, this is the third lecture in the fire science portion of the fire PRA class. And what I want to do this class is I want to briefly go over what we've talked about in the first two classes and then focus on this these topics here, which are, again, energy conservation, mass conservation, species conservation, and rules for gas mixtures. So, as we discussed last time, really over the first two lectures, what we've talked about was the evolution of a fire, the fact that in fire modeling we don't really describe the flame so much as we describe the impact of the flame in the combustion process, really on life safety issues and property damage. And what that really means is that we have to track the progress of the smoke and the heat and see how that affects both humans and also property within whatever structure we're evaluating and looking at. So let's just switch over to the tablet and start talking about this in a little bit more detail. So last lecture we spoke about fire modeling in general terms and the need to approximate the details of the flame by using a quantity called the heat release rate. So remember what we said. We said that if you have a fire within some compartment and what you're interested in is understanding whether or not people are going to be able to safely exit that compartment and also perhaps structural failure within that compartment. So there's some fuel packet that's burning within some compartment. The real questions are whether or not people are going to be able to get out of this overall structure as this filling process occurs. So at some time T1 we might have a distribution of smoke within a compartment like this. At some later time it's spilled out into the adjacent compartment and has started to fill that adjacent compartment and has, in this case, begin to exit the room with the fire in it. So from a modeling perspective, what we're trying to understand is the available safe egress time. So we're going to use that term throughout the class. So sometimes that's given the approximation A set. So we want to understand what the available safe egress time is for anybody that might be within a structure like that. To model that requires that, among other things, that we know what the heat release rate of the fire is at any given time. Okay, and the way that this is connected to the conservation equations is going to be made clearer, but what we have to do is we have to track mass momentum conservation for the products of combustion. From a property damage perspective or a failure perspective, the heat transfer processes from the products of combustion and from the fire to structural elements and to engineered infrastructure are going to be important also. So we're interested in the heat transfer modification to structural components, etc. So, of course, we'll talk about the fire resistance of the structure and of the engineered systems within it. All right, so so I told you that the details of the flame are less important than the overall transport of the heat and the products of combustion. That said, it's still important to understand a little bit about the details of the flame. And so we're going to talk about, again, this idea of a flame temperature and a flame as an interface and a little bit more. So this builds on some of the discussions here. So, in fact, what I'm going to do is let me just talk about the specific details of this lecture then. So we're going to explore / discuss how the conservation relations can be used for flame analysis. Going to discuss, again, gas property relations. And we're going to really point out, not do any details on it, how these conservation relations might be evaluated computationally. Okay. So the conservation equations really balance equations that we use in combustion and fire are, the primary one really is mass conservation, to energy conservation, species conservation. So this is chemical species. And finally, momentum conservation. Okay, so we can work either in a Lagrangian frame of reference or an Eulerian frame of reference when we talk about these different conservation equations, and we'll talk about what the differences are between working in Lagrangian or Eulerian frames of reference for these. So mass conservation, and as we'll use it in this class, in this lecture, we're going to really just focus on integral representations of this. So mass conservation can be best stated for a control mass system. So if we are focused on all the identifiable pieces of matter in some configuration, then this is what we call a control mass system. And so we've tagged all the different elements of this. And so we have, say, some tagged element of material. Again, at some t is equal to t0 that deforms because of flow or otherwise. We recognize that the mass associated with this is the same. And so in this control system, so the subscript S is the system, dms dt is equal to 0. So this is a very simple statement of mass conservation. So the mass is constant with respect to time. Now, this representation, the fact that we've identified and tagged and looked at these identifiable pieces of matter, this has been in a Lagrangian reference frame. And that's just a definition or a way that this is described. But if you think about it, if we're looking at the mass in, again, a fire where, again, I'm going to, these are my favorite drawings, so forgive me here. But again, if you're looking at the amount of mass that is filling a compartment, well, it's not so much that you're interested in that particular tagging each individual particle, so much as you might be interested in specifying the amount of mass within a particular region of space. So when we focus on a particular region of space, we call that an Eulerian representation. Okay, and now, even more importantly, we can call the particular part of space a control volume. So it's a volume of interest, and we can talk about the surface around it or the area around it as a control surface. Okay, so in the simplest case, imagine you have a pipe with some flow through it. So there's a flow of some fluid through this pipe, some velocity, u bar, some average velocity. And so we can ask ourselves, between some section 1 and some other section 2, what is the statement of mass conservation for that section? You say, well, that's kind of silly, but this gets us moving in thinking about more complicated problems. And it will help us think about the flame problem also. Okay, so without deriving it, let's say what control volume mass conservation is. So control volume mass conservation, and this can be derived in a number of ways, says the change in mass within the control volume with respect to time is equal to the mass flow rate in minus the mass flow rate out. So as we look at this between 1 and 2, m dot in is this m dot at section 1 minus m dot at section 2. So the dmv dt is our unsteady or transient term. And m dot is defined as a mass flow rate. With units of kilogram per second, just like the dmv dt also has units of kilogram per second. Okay. Now, let's think about some other definitions. We talk about steady and unsteady processes, and we all understand essentially what these things mean. Obviously, nothing is really steady because, on some time scale, everything changes. But what we're saying is that over some time scale that is short enough that measurements show that there's a small or negligible change in this property with respect to time, that we can call that whether quasi-steady or effectively steady. So for us, a steady process is one in which there are no transient effects. Said differently, or perhaps simpler, is one in which there are no changes in the properties with respect to time. Okay, so steady mass conservation for this problem would be that the mass flow rate in is equal to the mass flow rate out. And you say to yourself, boy, that's sort of a dumb result. Why do we need that for a fire class or a combustion class? And so here's an interesting use of this. So we said that what's a flame? A flame is an interface. Okay, so and a premix flame is an interface between reactants and products. So imagine that you have, again, this pipe where on one side you're flowing in fuel and air, so a reactant, and out of the backside, you're flowing out products of combustion. So this is some reactor. And for fun, we put our control volume surfaces over here. And you say, okay, well, what does that tell me? So there's a reaction process that takes place here. There's a conversion of fuel and air. So F is fuel. A represents air. We can generally call the fuel and air our reactants. So we have reactants that are converted to products. And mass conservation has to apply. So how does this help us in terms of interpretation and insight into this problem? Well, say that the reactants have a velocity u sub r. So this is the speed in a particular direction. This is of the reactants. The pipe cross-sectional area is A sub C. And the density of the reactants is rho sub r. So let's just make sure we have the units here. So meter per second, meter squared, and rho sub r is the density, the mass density of the reactants. Kilogram per meter cubed. Okay, so the definition of the mass flow rate, m dot, which we defined earlier, is rho r ur AC. So again, we have the mass flux rho u mr times the cross-sectional area. So what this mass conservation relationship tells us is that if we're interested in the velocity of the products and it's a constant cross-sectional area system, the velocity of the products is equal to ur rho r over rho p. Where, again, rho p is the product's density. So steady mass conservation at least provides us that insight that if this is a variable temperature system, it's really the density ratio or the temperature ratio, if it's constant pressure, that gives us the relative velocity of the products compared to the reactants. Okay, and so we're going to use that as we move forward in these problems. There are also going to be problems where we're going to talk about the transient effects in terms of the in terms of mass conservation. So let me just pull out the final form there. So the reason for the transient effects, why that's important, is because we're interested in perhaps the time it takes to fill a container, and so identifying this container filling time is obviously relevant. Okay. So the example problem, there it is. So So container filling time. Why is this related to fire? We'll see shortly. So earlier we said that dmv dt is equal to m dot in minus m dot out. So we can look at a problem, for example, in which we have a bucket that we have some flow into the bucket, and we're interested in knowing how long it takes to fill this bucket with this fluid. Cross-sectional area A for the can or the bucket. There's a cross-sectional area A1 with velocity V1 for this fluid, and again, this fluid is filling the system. And so there are really two different ways. There are lots of different control volumes that you can set up for a particular problem. And so the idea of a particular unique control volume is not necessary. So we can either ask ourselves, what happens if we set up? So I'm going to just draw two scenarios where we can analyze this problem. We can ask ourselves, what happens if our control volume is this? So you say, okay, well, what's the mass with respect to time of that versus a control volume where we're analyzing it, for example, like that. We can say, well, is there a difference in our description? There's not a difference in our final answers, fortunately, but there are some subtle differences in the problem. So in this case, if we fix this and we're asking how much water or fluid is contained within it, note that this is a fixed control volume. So the boundaries of this control volume are not changing. On the other hand, in this condition, the control volume is supposed to be nominally at the free surface, so this is a moving control volume. And it's a minor issue, really, but the subtle difference here is this, is that as we talk about what the mass flow rate into this system is, the mass flow rate is whatever is crossing the control volume, and when the control volume itself is moving, it's not just the velocity of the fluid that determines the mass flow rate in, it's the relative velocity between the fluid and the control volume velocity. So in this case, as it's filling, this control volume is moving upward, and so there's a relative velocity between it and the fluid coming in. In this case, it's purely the fluid velocity that's crossing it that the controls are m dot in. In both cases, there is no m dot out. So remember, again, our dm control volume dt, which we said was the mass flow rate into the control volume minus the mass flow rate out of the control volume. There is no mass flow rate out of the control volume. And so it's just the mass flow rate in. And depending again on the control volume choice that we have, our m dot in is either the relative velocity or it's this fixed velocity. And so in the case that we have it as the variable, the moving control volume, our mass flow rate in is equal to rho times u. So it's going to be a total u. So it's a rho times our velocity of our jet or fluid times the velocity of that fluid plus the velocity. So it's going to be really a minus minus W, so it's this plus W, where W is the movement of the control volume. So just to move this along, the mass of our control volume is going to be the density of the liquid times the area of our chamber, of our channel, times the height of the liquid at any time. So there's this HP. And W is just equal to dH dt. So when we look at dmCV dt, it's rho A dH dt. And when we put our mass conservation relationship together, we get, okay, so I'm going to just write the two pieces. Rho A dH dt, this is our overall dmV dt, and we have rho A1 V1 plus dH dt here. So identifying the pieces, this is W and this is dmCV dt. So when we put this together, we get that dH dt is equal to rho A1 V1 divided by rho A minus A1. And I'd like to talk about what this means. So let's look at a few limiting cases of this. And the thing that perhaps should be disturbing, so in fact, let's simplify this. It's A1 V1 over A minus A1, right? So you say, wow, that A minus A1 bothers me. And the reason it should bother you is you say, well, it says that if A1 is equal to A, this thing blows up. And that's okay, right? Because what we actually said was we said that we're asking ourselves, the HDT is really the rate of filling. And so we're saying that it matters if you have a pencil-thin amount of fluid filling up. So here A1 is tiny compared to A, which is the cross-sectional area of this bucket, versus a case where, say, A1 looks like that, and you have this big stream of stuff just filling this thing up, and, you know, pretty much it's going to instantaneously fill it up because this is rising so quickly that it just, you know, fills it up again very quickly. And of course, in the limit of A is equal to A1, it's already full. So dHdt is infinite. It's instantaneously full. So this is okay. That's exactly right. And so the whole point here is that you do have to be careful about the choice of control volumes, and you have to just be aware of what's going on. And so you say again, why is this relevant to fire? So relevance to fire. Remember those videos that I talked about last lecture? And so again, I'm going to apologize in advance, but in those videos, we show, again, a fire, and we show or see the descent of this hot upper layer. Well, from a life safety perspective, the most dangerous part of the fire is really the smoke layer because of its toxicity and the heat. So from an egress perspective, understanding how fast the upper layer descends is extremely important. And so calculations of the type that, remember what we said, and we're going to talk about this in much more detail later, that above the flaming part of the fire is called the plume. So the plume is the buoyant lofted products of combustion. Okay, gotta check my watch. Okay, and so that descent is important, and so the same ideas that we were talking about, and we'll show that the mass flow rate of the plume is a function of the fire heat release rate. So it says that if you know what the mass flow rate, if you know the fire size, you can get estimates of the plume mass flow rate. There's a process called entrainment here, so it's not a constant value because you're constantly mixing in air with this stuff. But that correlations that we'll talk about, we'll pull that out. And so we can figure out what the filling time is for a room that has a fire in it. All right, now let's talk about energy conservation. Now, I think we started at, let me just check the time, so make sure that we're running on schedule.
We got 37 minutes.
Okay, great. Okay, so let's do energy conservation. And so the basis of energy conservation is something called the first law of thermodynamics for us. So this is not, this doesn't, all the nuclear, electronic, and other energy modes are buried in internal energy for us. So this is energy conservation, and so we use the first law of thermodynamics. And what this states is as follows. It says that, okay, so let's have some definitions. Well, let's just talk about it in words first. It says the change in energy for a mass of material is equal to the amount of heat transferred to the material let's put net here plus the net amount of work done on the material. Okay, that seems to make sense. That seems reasonable. So the change in energy is equal to the net amount of heat that you put in plus the net amount of work that you do on the material. Okay, so how do we express that mathematically? So the expression of this mathematically is this first law. So the energy is what we would say composed of the internal energy plus and we're not going to really worry about the kinetic and potential form, so I'm going to put potential and kinetic, but these are typically negligible for our applications. M is the mass of material. U here is the mass-specific internal energy. Okay, so that's, I know that there are lots of different backgrounds for the people taking this class, so for those of you who know this, I know that I'm going over things that you know really well, but there are people with other backgrounds that don't know this material. And so this has units of kilojoule per kilogram, and it's a relative quantity, so it is a tabulated quantity for different materials. There are simple thermodynamic rules that we can use to understand what the change in internal energy is for particular materials, and we'll get into that shortly. Okay, so what we said is the change in energy, which for us now really is the change in internal energy, is equal to the net amount of heat that's put in plus the net amount of work that's put in. So this is the amount of heat energy and this is the amount of work. Okay. So again, this is formulated for an identifiable amount of matter. So the typical case we talk about here is, say, a piston cylinder system. So this is not the water, this is not the filling problem, but it's a piston with some, for example, gas inside that we are allowing heat to be transferred into it, and we are doing some amount of work on it, so we apply a force over a distance, and we ask ourselves what the change in energy is for that system. So this is, again, a piston cylinder system. Okay, we're less focused on these problems than we are, again, on, let's again go towards our pipe flow type problem. So we look at the Eulerian representation, and again, with some sort of flow in and out. So for this control volume, again, between 1 and 2, our form of mass conservation, so we're going to say for a, this again, we're going to say that that mass conservation for this problem okay, I'm sorry, give me 1 second here. All right, so the Eulerian representation of this is going to be dmu CV dt is equal to, and so here's, we're going to introduce another property called the enthalpy shortly. And so to identify that enthalpy property, we're going to have to look at the flow work that's associated with transporting fluid across the system boundaries here. So the first piece of this, though, is going to be an m dot in. And so I'm going to do it like this first. So I'll define these pieces in a second. Okay, so this is just really our flow processes across the control volume face. But what happens is that this w.net has a couple of different pieces to it. This w.net has a piece of it called the flow work, and a part that sometimes we call shaft work. So the shaft work is, imagine if there's, somebody has a propeller that's rotating in there and putting energy in like that. Now, to look at the flow work component, we ask ourselves, we say, look, on the boundaries of this system, again, it's a force over, so remember our work is a force over a distance, and our flow work is really the force effect with a velocity, with a flow, with a velocity on top of it. So when we look at that, we're really looking at a quantity that looks like, so we'll scale it like this. It looks like a pressure times the cross-sectional area times the velocity. So, yeah, we'll say V. So it looks like this quantity. So it looks like this net. Now, what we're going to do is we're going to divide by the density. And so we get something that looks like m dot times P over rho, where P is the pressure, and again, rho is the density. Okay, so this is perhaps a little too much detail, but let me just close with this then. So what we end up having is we get an m dot in times a un plus p over rho n minus an m dot out times u out plus p over rho out plus q dot net in plus w dot shaft in. There's a new property called this is the mass specific enthalpy. That is equal to the mass specific internal energy plus the pressure divided by the density. Now, P over rho is sometimes written as PV, where V is the mass specific volume. So if the density, okay, so the density is kilogram per meter cubed, the specific volume is meter cubed per kilogram. It's just really the reciprocal of the density. All right, and so again, the relevance to fire, for a problem like this. Is that when we talk about, again, we're going to talk about this reacting system, reactants and products, and we have this control volume. Let's imagine that we're working in a steady case. So remember, again, no transient terms. So what the first law says for this problem is that m dot n Hn plus q dot net in is equal to m dot out H out. And now I'm going to play with this just a second. Okay, so now what did I neglect? So we neglected W dot shaft, so we don't have a shaft coming out of this pipe. And we said it was steady, and W dot shaft is equal to 0. So make sure that when you look at this equation, you're happy with that, because all we did was we got rid of this guy, and because it's steady, we got rid of that guy. Okay, this is great. Again, time-wise, where are we? I think we're at, we started at, timer is not working. Okay, so I think we just have another minute or so. So why this is relevant is the case where Q dot net is equal to 0 is called an adiabatic problem. For that adiabatic problem, what we get is something that's interesting, and it tells us about the flame temperature. It says that Hn is equal to H out, or the enthalpy of the reactants is equal to the enthalpy of the products. Now, enthalpy for gases has an interesting property. So for an ideal gas, which is a good approximation for a lot of our problems, dH is equal to specific heat capacity times dT. This is mass specific heat capacity. All right, we're almost there. So when we plot the enthalpy as a function of temperature, it's not linear, but it has this variation where it increases with temperature because CPs are positive. And I mentioned before, I said, you know, the enthalpy of the reactants at any given temperature is higher than the enthalpy of the products. And I'm going to get back again and tell you now, okay, so if we're at, say, 25 degrees C, some reference condition, so we're going into this pipe with reactants at 25 degrees C. It's adiabatic, so we're in this isenthalpic system where Hn is equal to H out. If I just go over until I touch the enthalpy of the products, the temperature that the products will be what you might consider, and this is not to scale, obviously, so there's a scale break here, is what you would consider the adiabatic flame temperature. I'm going to say it differently. When the reactants when the bonds are broken on the reactants, a lot of energy, you can think about a lot of energy is released as they go to the product state. So there's a lot of heat that's available after the reactants are converted to this cold product that is then used to raise the temperature of the products. So those are the interpretations, and again, we need to do some examples on this problem. Okay, so let's stop the lecture here, and I promise that the next lecture we'll do more examples before we talk about before we talk about any more theory.